Hello, so we're going to talk a bit about superposition, diffraction, and interference. Was tuition, and the principle of superposition comes to you as the resultant displacement of the medium at any point in space is the sum of the displacements that each wave would cause at that point at that time. So what does this actually mean? So we've got the resultant displacement is the total displacement, so it's the sum of each wave, okay? A wave is a displacement in a medium, okay? So if we have two waves coming at the same time, so this wave plus this wave will give us this bigger wave. So we can see here what's actually happening is if this is our 0 point going through each of these, probably should have drawn these side by side, but no matter. This wave plus this wave, we've got a point here and a crest here. Both crests are going to give us one big crest. So that's going to be 2 times the amplitude. I'm saying that these are identical waves. Same with the trough is going to be 2 times the amplitude of the trough on these waves here. Okay, so whenever they come together and make a greater wave, we call this constructive interference. Okay. I've taken away half my letters. Oh well. Constructive interference. And then whenever we get our waves, and if you can think about these, whenever they add together, you're going to have a crest plus a trough, which is just going to cancel out to 0. Same with here and here, and then at this point it's going to be 0. So the whole way through, the total amplitude when added together is going to give us 0. So it's going to cancel itself out. So this is known as destructive interference. Okay, so there's some really interesting things you can do with this. For example, noise cancellation. If you think about the signals you get through headphones, you've got the signals that you want from the song that you're listening to, and then you've got a lot of noise in between. So active noise cancellation cancels out those signals by putting in a wave, an anti-noise wave of the same phase the same amplitude but opposite phase. Okay, so if you look at this a little bit more visually, here the addition is between the blue wave and the black wave. Okay, so at the starting point they're both at amplitude 0. So this is amplitude on the x-axis, and this is time on the right axis. So at the starting point you've got both of them at 0. The crest of this black wave, you've got the trough of this blue wave. So that's going to sum together. It's going to be the crest minus the trough, because if you think of this as a negative amplitude, so say this is -1 for example, and this is 3, then this is going to be 3 plus -1, so that's going to be coming in at about 2. Those are just arbitrary numbers, but you get the sort of general gist. At this point again, it's pretty much 0, and here it's going to be the trough plus the almost the crest of the blue wave, and that's coming in at a negative point here. So what we've got here is a large point of destructive interference right here, and then some points where it's destructive interference. Like here is an example. It's not total destructive interference, but it is taken away from the amplitude of this black wave. Okay, so it leads to some quite interesting experiments. So here is a picture of some water waves. So the stone's been dropped in about here and here, which creates a sort of ripple in the water. These ripples come together, and the crests of the ripples join with the crests of the ripples of, from stone A and stone B. So you've got crest A plus crest B, and it's giving us all these light points. And then the troughs come together as well and give us sort of destructive interference in these sort of dark holes. You can almost see them as dips, as holes in the trough. Okay. So if we were to look at that there diagrammatically, it would look something like this. It's almost like an optical illusion. And then if we think about passing monochromatic light through an aperture, then we would get a sort of curved wavefront, which if we pass through a double slit, we would get 2 curved wavefronts, which will then interact with each other. And we'll get constructive interference where the crests come together, and destructive interference where the troughs come together. Okay, so if we were to produce this onto a screen with light going through a double slit, we would have a sort of bright and dark pattern, and we call that the interference pattern. Okay, and this is actually called Young's double slit experiment, okay, because it's going through a double slit. Okay, so what we have is a central point maximum, where most of the light passes through, and that's our biggest constructive interference. Then we've got these other points of constructive interference. This will be the first order maximum, and these will be the second order maximums. Okay, so to visualize that a bit better, we've got the intensity is greater for the 0th point maximum, and then gets less and less the further you go along. So why do we need to know this here? It's quite useful. Basically what's happening is we've got waves with the same wavelength, but they're traveling different distances. So whenever the crests come together, we get a bright point, which here are just shown by dots on the diagram. So whenever the crests of these waves come together, we get a bright point. So at this point, the crests they're traveling the same amount, the same distance. So you're always going to get at the exact same. There's going to be no difference between the paths. So we're going to get constructive interference. To get constructive interference, we need to have an integer number of wavelengths coming through at each point. So to get to here, let's say we've got 1, 2, 3, 4 wavelengths. To come at a crest, we would need to have either 4, 5, 6, just an integer number of wavelengths to get constructive interference. To get destructive interference, the path difference between the two paths needs to be a half integer number of wavelengths. And this makes sense because if we think of a wave coming through like this, there's one wavelength. If we were to displace that by half and bring it through like this, quite hard to draw wavelengths, but you can sort of see that it should cancel out if it's a half wavelength. I think I drew a quarter wavelength there, but it doesn't really matter. Okay, so the wavelength given by plus the distance between the two slits times the distance between the 2 points over the distance between the two where the slits are and where the mirror is. If we know these three distances, we can work out the wavelength. Okay, and we can also therefore, if we know the slit distance and the distance from the mirror to the slits, and also the distance between our two slits, when we're able to work out the distance between our maximum points, our constructive interference points. And this is all to do with it having to come in at an integer number of wavelengths. Okay, so another thing with constructive interference, so we've got standing waves. This here is just on a string. So we've got 2 points and a string between those 2 points. So if you get the string and attach something that's going to vibrate or oscillate up and down, then you're going to be able to displace this string. And if you do that, if you do that at different frequencies, then at certain frequencies you will get a point where it will vibrate and then meet its reflection and then resonate with constructive interference. So the first point where it resonates, the wave will sort of look as if it's solid, and it looks a bit like this pattern. So it's going up and then down and then up and down and resonating at that frequency. Okay, and we call this the fundamental resonance frequency. Okay, so let's work out some maths to do with this frequency. The difference between our two fixed points where the string is fixed is going to be L. That's a difference L, and we can see here that that's half a wavelength. Okay, so a full wavelength would come back to where it started in the beginning, having gone through a crest and a trough. So L is equal to a half times our initial wavelength. Okay, from the wave equation, velocity is equal to frequency times wavelength, or here velocity is equal to wavelength times frequency. It's the same thing. And then we know that the wavelength is going to be equal to 2L. Okay, so one wavelength is going to be equal to 2 times the length. So velocity is going to be 2L times frequency. Then frequency is going to be velocity divided by 2 times the length. Using the same sort of maths with the second part, the first overtone frequency, or the first resonant frequency, we know that the wavelength is now equal to the length, so that makes it quite easy for the maths. So the F1 is going to be just equal to V over L. Then similarly, the second overtone frequency is looks like this pattern. Remember, of course, that it is vibrating, so the reflection's also there. And whenever you look at it as an experiment, the waves will look a bit like that there. Okay, and these are the equations for the second overtone frequency. It's worth figuring out how to do these. You just work out what the length is, and then what the length is relative to the wavelength, and you use the wave equation to figure out what the frequencies will be. Okay, so you're probably wondering what these N's and A's are. N means node, A means antinode. So an antinode are these bits where it's at constructive interference, and the nodes are the bits where it's at destructive interference. You can actually touch the nodes within the experiment, which is quite fun to do. Okay, but these aren't the only standing waves. We've also got standing waves in an open tube. So these are sound waves. This is supposed to be a loudspeaker, tube of length L. We've got these standing waves. So the first one will look like this. And if it's a sound wave, how do you know it's resonating? Okay, and you'll know it's resonating because it's much louder. Okay, it's noticeably a lot louder. So we did this. We didn't do it with a loudspeaker. We just did it with tuning forks, and we were just hitting the tuning forks, and that would give the noise, and you could tell when it's getting noticeably louder. So you're hitting tuning forks at different it's the same frequency, but you can change the length that you're hitting. So if you hit the tuning fork there, you might get a resonance. Okay, but in this case, the resonance comes, so this is our length, and the resonance is going to be here, so it's a quarter of a wavelength here, and that's equal to our length. So that lambda, or wavelength, is equal to 4 times length times the length of the tube, because that's, you would need 4 times this length to complete this wave. Okay, that's only a quarter of a wavelength. So then we can work out that the frequency is going to be equal to the velocity over 4 times the length. So work these out with the next modes of vibration. The difference between the tube and the standing wave. With the standing wave, went sort of node antinode like that, and then it started at a node and finished at a node. With the standing waves in an air tube, it starts at a node and finishes at an antinode. Okay, so we've got node, antinode, node, antinode here. Okay, so it's worth figuring out what will the next vibrational frequency look like, and what will the frequency be for both the standing and the open air tube. And it's worth figuring out how to work out how to do this maths. It's not overly taxing. Okay, if you have any questions, do let me know. Cheers.